One of the more common applications of the derivative is finding the equation of a tangent line. Now, as you can see here in green, this line is tangent to the graph in blue because it hits at exactly 1 point. Now, in order to write the equation of the line, we need to know a point where it hits, the actual point of tangency, and then we also need to know its slope. And of course, that's where the derivative comes into play, because the derivative tells us what the slope instantaneously at that one spot is. So the two steps is to figure out at a location what the y value is and what the slope is. So if we go ahead and take the y value and plug it in, we can look at this point as the ordered pair a, f of a, and they'll have to give you that spot so you know where you're doing it at. And then in order to figure out the slope at that point, we'll just need to take the derivative and evaluate it at that spot. Because again, the derivative will tell us the slope of the tangent line. Now, once we have that ordered pair and the slope, through the derivative, we can write the equation using point-slope form. That's the easiest way with this information to quickly come up with a linear equation. So as a reminder, point-slope form looks like y minus the y value. So in this case, it'll be the function value at our location. And that will be equal to our slope, which is the value of the derivative at our number, times x minus our x value. Okay, so again, point-slope form is going to be the easiest way. You're not having to do it that way. If you prefer slope-intercept or something else, that's fine. But this is the quick, easy way to do it because you just need the point, right, and the derivative to give you the slope. Okay, so let's try an example. We're going to find the equation of line tangent to the graph of f of x, which is x squared minus 5x at x equals 2. Now, the way I like to organize my work, and I'll kind of do over here on the right, is that I know that I have an ordered pair where the x is 2. I need to find the y value, and then I need to figure out what the slope is. And again, that's going to be the value of the derivative at 2. So an easy first step would be to just take my 2 and plug it in my function to figure out what that y value is. So in this case, if I plug in 2, that gives me 2 squared, which is 4, and plugging in 2 here gives me a 10. So if I take 4 minus 10, that's going to give me a negative 6. So the first thing I found out is that my y value here is negative 6. Now the next step is to figure out the slope. So that means I'm going to have to figure out the derivative. Now step number 1 is we need to make that calculation. So that means I'm going to take the limit as h approaches 0 of our f of x plus h minus f of x, and then divide that by h. Now, this is just the way I'm going to choose to do it because this is honestly the more common, application. However, since I am finding the derivative specifically at 1 point, I could use the other form of the derivative to calculate that. But I think it's really good practice with the algebra to do it this way, so I'm going to demonstrate that. So the value of the derivative is going to be that 2x minus 5. And I can use this function now to figure out what the value specifically is at x equals 2. So to do that, we're going to go ahead and take our derivative here and evaluate it at 2, which means we're going to take 2 times 2 minus 5 and tells us the value of the derivative is equal to negative 1, which by definition then is the slope of the tangent line. So now that I have my point and my slope, I can write the equation for the line tangent using point-slope form. So it's going to be y minus my y value, negative 6, which is y plus 6, and that equals my slope, negative 1, times x minus 2. Now, the next thing I want to talk about are graphs of derivatives. Now, this is where we visually draw all the values of all the slopes of a function. Now, the reason this is important is by looking at the graph of a derivative, we can see where we have positive derivative values and negative derivative values because that helps us identify where the slopes are positive and negative. And more importantly, it informs us where a function is increasing or decreasing. So the first thing I want to highlight is that, of course, given a derivative, a function is increasing when it is positive. So if the derivative is a positive value, those are positive slopes increasing. Likewise, the opposite is true for decreasing, right? When a graph is moving down left to right, that means the slopes are negative, and so is the derivative. Now, the other thing we're going to be using a lot with that is to identify maximum and minimum values of a function. Because if we can see where the graph will change from increasing to decreasing, or vice versa, those can identify where minimums and maximums can occur. And more importantly, those minimums and maximums are going to occur at locations where the derivative is equal to 0. And that's true because when you look at a graph, for instance, and I'm going to kind of pick on the one down here, this minimum happens when you have horizontal tangency. So obviously at that turning point, the slope is 0 instantaneously, and that can help you identify a location where you would have that minimum. Now, the other thing I want to point out just graphically is to see those intervals. Now, right now we don't need to be super strong at sketching the graphs, but we want to start to get a sense of what they look like. So in blue, as you can see here, this is the graph of f of x, whereas the green line here is the graph of its derivative. The first thing you should notice is, and it's very obvious on this one, is that the derivative is usually 1 degree less than the function. So my function here is a parabola, a second degree function, but it's a linear first degree function for the derivative. So that can help you kind of get the right shape. Now, the other conclusion you want to notice is that, for instance, in this region right here, okay, the graph that's in green, the derivative, right, is below the axis, which means the derivative here is a negative value. Okay, so it's less than 0. But also on this region, this is where the original graph f of x here is decreasing. So again, we see that connection where negative derivative, that means that our function f here is decreasing. Now the opposite is true on the other side, right? On this region over here, this is where the derivative is above the axis, right? So the derivative is positive, meaning the graph has positive slopes. And you can definitely see that here in blue because the conclusion you can make, of course, is that f is increasing. So this visually gives you that connection between when the graph is decreasing, we have negative derivative values. When the graph is increasing, we have positive derivative values. And in pairing that with the idea that the derivative is typically a degree less, you can help you kind of form an image of what that looks like. Down the road, our goal is to be able to look at the graphs of just derivatives and be able to analyze and talk about the graphs of f. Now, a special case in this I want to kind of throw out there would be if my original graph here in blue was linear. Well, a line always has the same slope no matter where you are, which means that the derivative of a line will be itself a constant value. So as you can see, this blue line here has a slope of 2, so anywhere, right, the graph has a derivative value of 2. So as you can see that we have this constant. And when that's the case, in this case you can see this is a positive value here, it's always positive 2, the graph is always increasing. Now, the last thing we want to talk about is the connection between differentiability, the ability to find a derivative, and continuity. So what we know is that if you're able to find the derivative at a point, then we also know the graph is continuous at that point. It's kind of a conclusion we know is true. So in other words, differentiability implies continuity. So in the future, you might notice directions, theorems, explanations say things are differentiable, and you should also imply in your mind and know if that means they're also continuous at that point. Now, what I want to talk about are some special places where we have points that are non-differentiable, okay? Which means that there are certain situations, certain things happening in graphs where the derivative does not exist. And we need to be aware of these when working with functions because of that situation. Now, the first one is if you have a point of discontinuity, okay? A hole, a break, or an asymptote. If you have that sort of thing happening, you're not going to be able to make tangent lines at those spots, so the derivative does not exist, okay? So that's the easy one. Holes, breaks, asymptotes, the derivative is not going to work there. Now, the next two are going to be kind of interesting because sharp turns, things that are called corners or cusps, they are continuous. The graph exists there, and you can sketch it without lifting your pen or pencil, but the derivative doesn't. So my illustration here for an example is the graph of the absolute value. Now, this is the absolute value here, and you can definitely tell that there's a sharp corner here at 2. Now, the graph of its derivative looks like this, and clearly you can see a break in the graph where there is no value of the derivative here at 2. And that's, again, that sharp corner. Now, the reason for that is that when you look at the graph of the absolute value, to the left of 2, it's always the line, right, that's -1 slope. Whereas on the other side of 2, it's always a line with a +1 slope. So looking at the graph of the slopes, in this case the graph of the derivative, we can see they don't line up and connect. So while the derivative is always -1 to the left of 2 and the derivative is always +1 to the right of 2, there is no value at 2. Right? They don't line up, it's never going to work. So even though this is a continuous graph, at 2, that's a point of non-differentiation where the derivative does not exist. Now, our last example is the situation of vertical tangency. Again, this is going to be a continuous graph that you can draw without lifting your pen or pencil. But at that instant, when the slopes become undefined, right, when they kind of go vertical just for an instant, there is no derivative because being vertical means the slope is undefined. You're dividing it by 0. And since the derivative is the slope, it means the derivative does not exist. Now, my example here is you can see this graph at 0, we have a spot just for an instant, right, where the rise over run goes vertical. Okay, and so at that spot, if you were to look at the derivative, we have a vertical asymptote. Again, a place where the derivative does not exist. Okay, so any discontinuity, any sharp turn, corners and cusps, or vertical tangencies, they are places where derivatives are not going to work, and being aware of them will help us do our work in the future.